So it gives me a great pleasure to welcome today's speaker, Professor Ganesh, for his special lecture, it is a IMSc popular lecture, and also celebrating 60 years of IMSc, and also the 75 years of independence. So it's a great pleasure to welcome Ganesh. So I want to say a few words about Ganesh. So Ganesh is I'm very fortunate to have him as a collaborator at Math Science. So Ganesh is a very distinguished quantum magnetism person. He works on a variety of problems in quantum magnetism and also in problems in decay model and various things. So he has a knack of choosing nice problems and solving them as well as possible. And he has a knack of attracting lots of young students. Apparently he's a very popular guide at Math Science. And so Ganesh did his undergraduate at BITS Pilani, and then he did his PhD at Toronto University, and then he was a postdoctoral fellow at Max Planck in Dresden, and then he joined us. We were very fortunate to have him so far. And for personal reasons, he decided to go to another beautiful place, Brock University in St. Catharines, one of the most beautiful places in Canada, near Niagara Falls. I tell him that nothing to beat our Marina Beach or Kottiwakam Beach, but he doesn't agree. So I wanted to say a few things about Ganesh. Okay, I think I'll allow him to speak. He will speak for himself.
Yes.
So it's a pleasure to welcome Ganesh.
Thank you, Professor Bhaskaran. So Professor Bhaskaran was one of my first mentors, so it's very nice to be introduced by him. Thank you all for coming, and I'm told you have to stay until the end of the talk to get refreshments. So I hope you'll stay here for all of the talk, Good, so I will tell you about emergence and indecision in the world of quantum magnets, some interesting work, hopefully interesting to all of you. So as Professor Bhaskaran mentioned, I was at Math Science for about 5 years, and then I moved to Brock University fairly recently. This work, the bulk of this work was done at Math Science. So this is work from Math Science. And a lot of it is with my student, Shubhankar Khatwa, who's now doing his postdoctoral fellowship in Canada. There was a very enterprising undergraduate student, Sarvesh Srinivasan, who spent 2 summers here, and Professor R. Shankar and Professor Bhaskaran here at Math Science have also contributed, and Professor Deeptiman Sen from IISc was also involved in some of this work. So I'll tell you about this. I will explain what all these words mean. I'll explain what quantum magnets means. I'll explain what emergence means. I'll explain what indecision means, at least what I mean by these words. Good, so let's start. Okay, so let's start with the story. So this story is a very famous concept in Buddhism, in early Buddhism, called the chariot simile. So this is from a text called the Milinda Panha, which is dated to about 100 years before Christ, 100 BC. So the context is there is a king, so King Menander, who is an Indo-Greek king. He goes and meets a Buddhist hermit in the forest, Nagasena, and they have a conversation. The king challenges Nagasena, and then this conversation ensues. So let me just read it. So Nagasena asks, "How then did you come, on foot or in a chariot?" Milinda responds, "I did not come, sir, on foot. I came in a carriage." "Then if you came, sire, in a carriage, explain to me what that is. Is it the pole that is the chariot?" Milinda says, "I did not say that." "Is it the axle that is the chariot?" "Certainly not." "Is it the wheels or the framework or the ropes or the yoke or the spokes of the wheels or the goad that are the chariot?" And to all these he answered, "No." "Then, is it all these parts of it that are the chariot?" "No, sir." "But is there anything outside them that is the chariot?" And still he answered no. And finally Nagasena says, "Then thus ask as I may, I can discover no chariot. Chariot is a mere empty sound. What then is the chariot you say you came in? It is a falsehood that your majesty has spoken, an untruth. There is no such thing as a chariot." Okay. It's a provocative philosophical argument. You can extend this to everything. You know, a building that we are in is made of bricks, of cement, of mortar, of wood. Outside of these, there is no building, and yet each of these is not the building. So clearly there is no building. There are bricks, there is mortar, there is cement, so there is no building. You can talk about an atom. An atom is an electron, proton, electrons, protons, neutrons. Each of them is not the atom. There is no atom outside of these parts. So clearly, there are only the parts. The atom does not exist. Okay? You can extend this to everything in the world for that matter, right? So every scientific discipline has to respond to this argument in some way, right? So let's present that a variation of this argument. So let's consider three objects that we're all familiar with. Say raindrop, a water molecule. So the red dot is oxygen. There are two hydrogens, so that's H2O. So that's a water molecule. And then we have an iceberg. So clearly, these are three very different objects. Right? So if you're a physicist studying them, you would study them very differently. So there would actually be three different types of physicists studying them. Right? So somebody studying a raindrop might ask the question, what is the shape of a raindrop? Right? So it turns out that's a very interesting question, and the shape is definitely not that. So we've all been lied to since childhood. Raindrops don't look like that. They look more like a hamburger bun, or as I've been told, more like a badusha for the high tea that we will have later. Right? So that's the actual shape of a raindrop. And if you're a physicist who has to study that, you would use surface tension to study that. That would be the prime concept that you would use, the most important concept you would need. Right? If you're a physicist studying a water molecule, you might ask, what is the most precise value for its dipole moment? Water molecule is polar, has a dipole moment. You might want to estimate that. You might use quantum chemistry, which is a very sophisticated numerical solutions to the Schrodinger equation to answer that question. Right? If you're a physicist studying icebergs, you might ask, what's the lifetime of an iceberg? If you want to tow one from the Arctic Ocean to the Middle East for fresh water, will it survive the journey or not? That's an important question, and so you might want to answer that. The concept you'd use there is heat transfer, so you'd have to estimate this. So clearly, there are three different objects. The questions you ask are very different. The concepts you use are very different. The techniques you use are very different. And yet, they're all water. Right? The raindrop is water, water molecule is water, iceberg is water. Right? And yet, they are so different. They bear no resemblance to each other. Right? So are they all the same, or are they different? That is another provocative question that we might want to answer. Okay, so as a physicist, the answer to these questions, does the chariot exist? Is water the same or is water different? Comes from a concept called emergence, which we can define as follows. We can say, if you have a collection of entities, and if you are at a certain scale and at a certain complexity, at a certain level of complexity, if you may, then the collection of entities acquires an effective description. So let me explain what I mean by that. A scale, by a scale I mean a window in a space of dimensions. So a certain range of sizes, a certain range of temperatures, pressures, and so on. So that's a scale. Complexity denotes the number of participating entities. So how many entities come together? So in the case of a chariot, you have two wheels, one axle, one platform, one yoke, and so on. Right? So that's the assemblage of parts. And it's not just the number of parts. So clearly, you just make a heap of them. That's not a chariot. Right? So they have to be related to each other in certain fixed ways. Right? So complexity denotes both the number of participating entities and the relations between them. So that's all encapsulated in this term. Okay? So let me explain. So let's just take this example. So let's take the water molecule as our unit of choice. Right? So if I have water molecules, a collection of water molecules, at about 25 degrees Celsius, at about a length scale of about 3 millimeters, that defines a scale. Right? And if I have about 50 milligrams worth of water molecules, that defines the complexity. That's the number of participating entities, and the way they interact is well known. They interact with van der Waals forces. Right? Then this defines a scale, this defines the complexity. With this scale and this complexity, the collection of water molecules becomes a raindrop or a water droplet. And the same way, you have, say, minus 20 degrees Celsius, about 500 meters. That sets the scale. You can add pressure, and et cetera. You can add more dimensions if you like. And you have about 10 to the power 9 kilograms worth of water molecules. You get an iceberg. Right? So at this scale and this complexity, the collection of water molecules becomes an iceberg. So the raindrop or an iceberg is an effective description. Right? So essentially, it's an independent object. If you want to study a raindrop, you can forget about water molecules. You can just write down the physics of raindrops, you write the laws that you have, study whatever, answer whatever question that comes to your mind. Right? Similarly, an iceberg is its own object. It obeys independent rules, it obeys independent equations, and you can study it. Good. So this notion is emergence. So how does this collection of objects take on a new identity? So that's the focus of this talk. Right? So just to emphasize this, let's ask two hypothetical questions. So here's the first hypothetical question. Suppose you have a Jovian alien. Jovian is the adjective for somebody who lives on Jupiter, apparently. So you have an alien who lives on Jupiter. So Jupiter is a gaseous environment. There are only gases, there are no liquids there. Suppose there's an alien there, and the atmosphere of Jupiter is known to have water. So this alien has studied water molecules to great detail, let's say. Right? Will this alien ever know of a raindrop, or will this alien ever be able to even imagine that a raindrop exists? Right? That's a question we can ask. That's a hypothetical question. So here's another hypothetical question. So we all know that the Titanic crashed or capsized after it hit an iceberg. So suppose you have soft icebergs, then the ships will not be damaged. So I want soft icebergs, let's say. Let's say I'm some evil genius who wants to design soft icebergs. Right? Can I ever make soft icebergs? Can I ever engineer an iceberg that will be soft to collisions? Let me just ask this as a hypothetical question. Right? So clearly the answer to both of these is no. At least that's what I would imagine the answer is no. Why is the answer no? The answer is no because emergence, this process by which a raindrop appears or an iceberg appears, is a highly nonlinear process. It cannot be predicted or controlled. Right? If you're an alien who knows water molecules, you cannot even imagine, you cannot even do the calculation because you have 10 power 23 molecules together. That calculation is impossible to do. You'll never be able to guess that a raindrop forms. Right? And similarly, well, you can't even calculate it, then how can you predict or how can you design something? Good. Okay, so in general, emergence is a nonlinear process, highly nonlinear, cannot be predicted, cannot be controlled. But nevertheless, we would like to do this. So with knowledge of microscopic entities, so let's say we know the analog of the water molecule, any analog that we have. Let's say we know its properties very well. We would like to predict the effective description that emerges at a certain scale and complexity. That would be nice. Okay. And we would also like to design bespoke effective descriptions. Say we want to have some kind of soft iceberg. And I would like to at least have a pathway to start thinking about it. How can I even design it? So in general, these are very hard. This is impossible to do. However, in a limited way, with quantum magnets, these both might be possible. Right? You might be possible to predict emergence. It might even be possible to control emergence, to design emergence. Right? So that will be the rest of the talk. So I'll try to explain this. So, and in all of this, geometry, simple mathematics plays a very important role. So there's some nice pictures. Hopefully you'll follow along. Okay, so that sets the stage. And of course, this is a physics talk, but it's also a popular talk. So you'll need to know some physics to understand the rest of the talk, although I see most of you are physicists. Nevertheless, so there are two prerequisites for this talk, only two. So I'll explain the two prerequisites you need to know to follow the rest of the talk. Okay. So here is the first prerequisite. You'll need to know what is a magnet and what are spins. So for the purposes of this talk, a magnet consists of spins. Anything that consists of spins is a magnet. And a spin is simply an object that spins, an object that carries angular momentum. A top, for instance, is a spin. Right? Of course, we're interested in things like electrons that have spins. But for now, you can think of everything that spins, like a top is a spin. Okay. So in physics, we have two ways of understanding spins. One is a classical way, one is a quantum way. So I'll just give you a brief description of both. So a classical spin is simply an angular momentum. So if you have a top that's spinning, you can put your thumb along the axis where it's spinning, and you can use the right hand to determine the sense in which it's spinning, either this way or that way. So, and then roughly the velocity with which it's spinning sets the length of the angular momentum. So the direction is set and the length is set. So you get one vector at the end of the day. We call that vector angular momentum. So it's a vector, and it's a three-component vector. We live in three-dimensional space. So there is some x component, y component, and z component. There is some length of this vector we call the length s. Right? And because, as you might know from spherical coordinates, any vector in 3 dimensions, you can use 2 variables, some polar angle and azimuthal angle, to describe a classical spin. Right? Okay. On the other hand, you have a quantum spin. So within quantum mechanics, when you try to explain angular momentum, there are some restrictions. So a spin is described by 2 numbers. S and M. S is the analog of the length here, that's called the spin quantum number, or the total spin quantum number. And M is called the Z component of the spin. So essentially that's the analog of the Z component of the spin. How much of the spin is along the Z direction. Right? And in quantum mechanics, these numbers cannot be arbitrary. They must follow certain rules. So S can either be a half integer or an integer. So S can be something like half, 1, 3 by 2, 2, 5 by 2, 3, and so on. Right? So it can only be those numbers. So if you have questions about this, you can ask me later, or you can take a course in quantum mechanics. I'm sure you'll enjoy it. Right? M is another quantum number. M always goes from minus S to S. So you have to say S is 3 by 2. Then M will go from minus 3 by 2 to plus 3 by 2 in steps of 1. So you'll get minus 3 by 2, minus 1 by 2, 1 by 2, 3 by 2. Right? So in general, the Z component of angular momentum is discrete in quantum mechanics. It can only take certain values. And it can take values ranging from minus S to plus S in steps of 1. Good. So angular momentum is quantized or discrete. It takes discrete values along the Z direction. Okay. So these are the two things you need to know about magnets. Okay. So that's prerequisite 1. And just in case you're confused as to why there are two descriptions, you can reconcile them. A quantum spin with very large S is equivalent to a classical spin in a certain way. So there is a well-defined equivalence between them. Right? So if you're not worried about that, great. You shouldn't be for this talk. Okay, so here is prerequisite 2. You'll need to know some quantum mechanics. So this is a crash course in quantum mechanics, or just a very basic one-slide introduction. And we'll just take one toy model. Let's imagine we have a circle, and we have a bead on a circle, or a particle that is rolling around on a circle. So how do we describe this in quantum mechanics? Okay. So in classical mechanics, you can simply say the bead is here, maybe it's moving at some velocity going downwards. You can do that. In quantum mechanics, you cannot say that because the particle or the bead can be present at various positions at the same time. It can spread itself. Quantum mechanics allows for that. So the way we describe that is by using a wave function. So it's a complex valued function. So let's say the circle is this way. And we can introduce a coordinate x. So x is 0 here, x increases this way. And when you reach here, x becomes L, but it's periodic. So after L, you go back to 0. So it's just a periodic space. So that's the same space just opened out. So x goes from 0 to L, but it's understood that it's periodic. So the bead goes around, moves on this space. So on this space, you have a wave function. You have psi of x. So every value of x, there is some complex number that defines the wave function. And the way to understand this is it describes the probability of finding the particle. So you take some small interval between x and x plus dx. The probability that the particle is in that interval is given by the mod square of that complex wave function. So it just tells you how the particle is spread. Right? If it's peaked somewhere, the particle is more likely to be there. If it's very less somewhere, the particle is very less likely to be there. Okay, good. So let's continue with this. So how do we find out where the particle is, or what is the wave function of the particle? So there is quantum mechanics has well-defined rules. So we have the Schrodinger equation, and this is essentially the equation. The second derivative of this wave function has to give you back E times the same wave function. And E is the energy of this wave function. So if you don't worry about, if you're not particularly interested in this, don't worry. You just need to know the final statement of this. Okay. So the Schrodinger equation has solutions which are of this form. They're just wave-like solutions, e power I kx. Right? And because its space is periodic, you go to 0 to L, you come back to the same starting point. This k that you have cannot take arbitrary values. It has to take discrete values. Okay? And k has to take these values, 0, 2 pi over L, 4 pi over L, 6 pi over L, and so on. Right? It can also be negative, but okay. So in general, this k that you have can be 2n pi over L, where n is any integer. So we say that every solution here is associated with one value of k, or is associated with one integer n. Right? So the particle can only be in these states, cannot be anywhere else. So the particle state, I can give you an integer. It can be described by one integer. Okay, good. So now let's ask what's the energy of the particle. So the energy of the particle, if you just use this formula, you find the energy. So the energy turns out to be some constant times n squared, where n is an integer. So this is the key part you have to note if you're not interested in details of quantum mechanics. So what is the energy of a particle on a circle? It is n squared, where n is an integer, So the lowest value that can take is n is 0. So n is 0, you can get one state. The next higher value you can have is n is 1 or minus 1. In that case, the energy will be proportional to 1, n squared. Then the next value will be n is 2 or minus 2, then the energy will be 4. Then is 3 or minus 3, energy will be 9. 4 or minus 4, energy will be 16, and so on. Right? So you'll have one lowest energy state, which we call the ground state. And after that, every state is doubly degenerate. You have pairs that have the same energy. The energies go as squares of integers. So 0, 1, 4, 9, 16, 25, 36, 49, and so on. Okay? So those are the two prerequisites. With those two, you can follow the rest of the talk. Okay, so here is the crux of this talk. Okay, so I'm trying to convince you that there is an emergence principle that works for quantum magnets. So this emergence, this highly nonlinear, unpredictable process, when it comes to quantum magnets, follows a very simple rule. Okay, and this is the rule. It sounds complicated, but I'll explain it as we go. The rule is this. Let me just state the rule. A quantum magnet at low energies resembles a single particle that moves on the space of classical ground states. Okay. Might seem like a complicated statement, but I will explain it to you with examples. Okay. So this is a statement, but this is a very powerful principle. Right? And we have given a proof of this principle. In a way, this was known before, but hasn't been stated in this way. So we've given a proof of this principle in this paper in 2019. So the advantage of this is this statement applies to a wide class of systems. So many quantum magnets. It's not just one material or different materials. It's a whole family of materials. The second thing is it provides a systematic way to find the emergent picture. Like, we asked, you have a collection of water molecules. Do you get a water droplet? Do you get an iceberg? Do you get a snowflake? Do you get something else? Here is there's the analog of water molecules is spins. And you can get various objects like raindrops, snowflakes, or icebergs. And this principle tells you how to find that. So there is a systematic way to do it. Okay. And not only that, because there's a systematic way, it guides us when we want to design something useful. It says, you want that, then maybe you should start with this. Right? So there is a prescription to think about this. So that's why this is interesting. It's good. So I will explain this to you with examples. Hopefully you'll be convinced at the end of the day. Good. So with some good. So to explain this, for this talk, I'll take 3 simple toy magnets. There are molecular magnets that are similar, but these are essentially toy magnets chosen for simplicity to illustrate this principle. So they're not real magnets. Right? So I first take a simple magnet with just 2 spins. Then I take a magnet with 3 spins. Then I take a magnet with 4 spins. Okay. And let's say the spins are arranged like this. Here they just form a dumbbell. Here they form an equilateral triangle. Here they form a tetrahedron. Okay. And now the spins interact. They talk to each other. And the way they talk to each other is as follows. So in the classical scheme, in the classical way of looking at it, the energy is given by this. So we say this is an XY coupling. Right? So suppose I have 2 spins. So this spin is pointing that way, and that spin is pointing some other way. The energy of this configuration is given by this formula. So all I have to do is I have to just take the x component of the first spin and the x component of the second spin, multiply that. Y component of first spin, y component of the second spin, multiply that, and add. Right? So essentially, I'm just taking the xy component of spins and then taking dot products of that. Right? Okay. So again, if this is complicated, don't worry about it. So classically, at the end of the day, for all these 3, there is a very simple rule. Suppose I want to minimize energy, then I have to do 2 things, only 2 things. I have to take all the spins. Remember, classically, spin is just a vector with 3 components. So all the spins have to add to 0. So I have to have, let's say here I have 3 spins, so I have 3 vectors. 3 vectors must add to 0. The second condition is all the vectors should lie in the xy plane. So it's really a very simple geometric problem. I have n vectors that lie on a plane, on 2-dimensional plane. So n can be 2, 3, or 4. Sorry, n can be 2, 3, or 4. N vectors on a plane, they have to add to 0. That's it. Right? But you see that this simple statement is actually not so trivial, has very beautiful geometry behind it. Okay, so we'll go through this step by step. So let's first do the 2-spin case. I have 2 spins. The energy is given by just this. So how do I minimize the energy? Again, both spins should lie in the xy plane. Let's say the screen is the xy plane. Both spins are in the xy plane. And their sum should be 0. Right? So that means if the first spin is pointing this way, the second spin should be opposite. Only then, if I add them, I'll get 0. Right? Good. So this is one configuration that minimizes the energy. Right? So we say this is a ground state. Okay. So the next question I ask is, how many ground states are there? Okay. So the number of ground states is infinity, because I could have put the first spin in any direction. I could have changed this angle phi, so the first spin could be pointing in this direction, for example. The second spin will simply be opposite. So I can move the first spin, the second spin will be dragged. As long as they're opposite, it doesn't matter, energy is minimized. Okay. So I can say that, so I have a set of classical ground states. That set is parameterized by one angle phi, and phi goes from 0 to 2 pi. Right? So the space of classical ground states, the set of classical ground states, is equivalent to a circle. So any space that's parameterized by one angle is a circle. So in that sense, a set of ground states is a circle. Okay? So everything here is classical. I took this magnet, and I take a classical view of the magnet, and I say the ground states form a circle. Okay, good. Now let me take the same magnet and look at it with a quantum lens. So quantum mechanically, how do I solve this problem? Again, if you're not familiar with it, don't worry. Quantum mechanically, there is a well-defined way to solve this problem. So we write a Hamiltonian matrix or Hamiltonian operator. It turns out, so the number of possible states for the first spin is 2s plus 1, for the second one is 2s plus 1. So the number of states for both spins together is 2s plus 1 square. So we write a Hamiltonian that's a matrix of this dimension, 2s plus 1 square. We diagonalize that matrix, and the eigenvalues are the energies. Okay. So if you don't care, don't worry. There is a way to find energies. We can find energies. Okay. And we do that. Okay. And here is the answer. Okay. And this is where some magic happens. Okay. So we've solved the energies using quantum mechanics, and we get a whole range of energies. So the whole spectrum of energies, there's some bandwidth. That scales is about Js squared. So the maximum to minimum, that range is about Js squared. But let me only focus on the low energy window, only the very low energy states. Okay? And then I zoom in, and this is the plot. This is the result. This is the actual result we get when we do the calculation. Okay? And you see the x-axis is simply counting the states. So there's a first state, second state, third state, fourth state, fifth state, and so on. Okay? Y-axis is the energy. I've chosen the units in some funny way. Don't worry too much about it. It's just for convenience. So when you choose the units like this, something very nice pops out at you. See? So you see the lowest energy state is unique. There is only one state that has the absolute lowest energy, and that energy is 0. The first excited state actually has 2 states. I hope you can see this clearly. That energy is 1. The second excited state again has 2. That energy is 4. Then you have 2 with energy 9, 2 with energy 16, 2 with energy 25, 2 with energy 36, and so on. Right? This is precisely the energies of a particle on a circle. Okay? So I took a quantum view of the magnet. I've solved for its energies, and I find some energies. And if I look at very low energies, so that's like setting the scale. Right? I only want to look at very low energies. I'm fixing a scale. If I do that, the energies look exactly like that of a particle moving on a circle. Okay? So my claim is this is emergence. Right? I have only 2 spins. It's a very simple system. The complexity is very small. I have only 2 spins. I've set the scale. Scale is low energy. And now it looks like a completely different object. It looks like a particle moving on a circle. Just like a collection of raindrops looks like, a collection of water molecules looks like a raindrop. Raindrops' rules are completely different from water molecules' rules. The same way, a collection of 2 spins looks like a bead rolling around on a circle. Right? And if you did experiments, suppose you could only look at very low energies in your experiments. You can only, suppose you're doing some spectroscopy, you actually cannot tell the difference. The energies look like this. It might as well be a bead rolling on a circle, or it could be a magnet. You cannot tell the difference. Right? So the magnet has truly taken on a new identity. The identity is a bead moving on a circle. Right? Of course, this is a toy model, an example designed to illustrate this. It's a very simple illustration. Okay? So good. So please feel free to stop me at any point. Yes, please. Could you just say that again?
The spectrum.
Yes?
The spectrum is gapped for both odd and even spin?
Spectrum is gapped?
Like for both odd and even spin?
It looks the same, yes. Yes. It looks the same. You have to choose the units slightly differently for every S, but odd or even does not make a difference. Yes.
And that equivalence to where you are taking this equivalence to that bead problem. So
that also works for both odd and even spin. Yeah, both half integer, even, odd, it doesn't matter. It works for all S. There are some caveats to that statement that we can discuss separately. Okay. Yes, good. Yes, good. So it depends on how this, what is small, low energy. So there is some window that this window size depends on what S is, but otherwise it's the same. Okay, so I'm glossing over some details here. Okay, so let's take one example that's a bit more complex. So just to remind you again, the principle I'm trying to illustrate is a quantum magnet at low energies resembles a single particle that moves on the space of classical ground states, right? So I claim to have demonstrated that with this very simple example. I had a quantum magnet with 2 spins. The classical ground states form a circle. The quantum magnet at very low energies looks like a particle moving on a circle. Okay. So this is the proof of the equivalence in the simplest case. Okay, I hope that's clear. Okay. Okay, feel free to stop me if you like. So let's make it a bit more interesting. Let's take the next example. Suppose, let's say we have 3 spins. Right? And the 3 spins, so we have increased the complexity now. We have 3 spins in our toy magnet, and the spins talk to each other. And if I take the classical point of view, the energy is again given by this xy dot products. So the same way as we did just for one pair of spins earlier. Now I have 3 pairs. I have one interaction for this, one interaction for that, one interaction for this. Right? So I write the energy like this. But once again, to minimize the energies, the same rules follow. All 3 spins should lie on the same plane, xy plane, and they should add to 0. Okay? Now, we know there's a geometric way to do vector addition. I can simply start from the origin, draw the first vector, then draw the second vector, draw the third vector, put the vectors head to tail, and if the sum is 0, at the end I should come back to the starting point. Right? That's how we do vector addition. So that's my condition. The 3 spins should add to 0. So essentially I should do this, and come back. Okay? Now you can convince yourself that if the spins have the same length, then this should necessarily form an equilateral triangle. There's no other way. Right? Otherwise, you won't come back to the starting point. Good. So to minimize energy, you should form an equilateral triangle. So now I have formed an equilateral triangle here, spin 1, spin 2, spin 3. And now again, let me ask, how many ways can I do this? Okay. So here is one way. I can simply just change this angle phi 1. I can just rotate spin 1 maybe somewhere, and then spin 2 will also follow, spin 3 will also follow. The whole object will rotate. Right? That's allowed. So essentially, I have one angle that I can change. Right? Okay? But turns out there is one more possibility. Right? And this is the other possibility. So here I have spin 1, spin 2, spin 3. Here I have spin 1, spin 3, spin 2. Right? The order is switched. Right? And you can again look at this and see that you can rotate this as much as you like. If you rotate this, you'll never get this. So these two are actually sort of mirror images of each other. They're chiral copies. So you can take this and you can rotate it, as in you can change the angle phi 1. Or you can start with this and you can change the angle phi 1. And in both cases, you'll get ground states. Right? So I hope you're convinced. Okay? So the number of ways of minimizing the classical energy can be characterized like this. You have 2 discrete choices, each with one free angle variable. Right? So I can either do 1, 2, 3 or 1, 3, 2, and in each case I have one angle. Right? So this is equivalent to having 2 distinct circles, because here I have one space characterized by one angle. Here I have a different space characterized by one angle. So I have 2 separate circles. Right? So the space of classical ground states is 2 separate circles. Okay? Because that's the classical view of this magnet. So now let me look at the quantum view. Okay? So here once again I have the quantum Hamiltonian. I can write a matrix, I can follow the quantum machinery, and I can generate the eigenvalues. And here is the answer. Once again, I'm only showing the very low energy and eigenvalues. So you can see that the lowest energy state, there are 2 that have the same energy. That energy is 0. It's a bit crowded there, that's why I've written 0 here. Then the next set of energies there are 4 of them that have the same value, and that value is 1. Then you have 4 that have a value 4. Then you have 4 with energy 9, 4 with energy 16, 4 with energy 25, 4 with energy 36, and so on. Okay? So this is a spectrum of one particle that can live on 2 circles. Right? So imagine there are two circles and there's one particle. The particle can either stay here or there. So you have some energies here, some energies there. So essentially the number of states just gets doubled. So this is precisely the same as what we had before, except the number of states is doubled. So 2 in the minimum, 4, 4, 4, 4. Right? Okay. So once again, what I'm showing you here are the energies of the quantum magnet. But if you look at them, the energies are indistinguishable from a particle that lives on two circles. So once again, this quantum magnet, if you choose a certain scale, very low energies, it looks like a particle that lives on two circles. You do an experiment, you cannot tell them apart. Of course, if you do high energy experiments, you can. But just like, you take a chariot, you shoot a bazooka at it, it will not function as a chariot. Right? You're only supposed to use a chariot gently, about 30 kilometers per hour. You cannot run roughshod on it. In the same way, you look at this magnet at very low energies, it looks like a particle that lives in two circles. So once again, my claim is this is an emergent picture, and the emergent picture follows this principle. So I'm illustrating this principle once again for you. Right? So the XY trimer, which is this magnet, at low energies looks like a particle that lives on two distinct circles. So this is another nice example of emergence. Yes, please. Yes. Yes.
So you are doing quantum mechanics to find the energy of the quantum magnet.
Yes.
Then you are saying that it is matching to another different system.
Yes.
So before doing all the mathematics, is there any physical motivation that it should match to another problem? Is there any physics interpretation to that?
Yes. So essentially, this is the principle, right? So perhaps you're asking, where does this equivalence come from?
Yeah, the physics
right?
part. Yeah. So.
Yes. So there is a physics part, and I've ignored that in this talk because that will not fit in a popular talk.
Okay.
So there is one way of looking at it using a path integral equivalence between them. So you can write a path integral for a quantum magnet, and in low energy limit, it looks exactly like the path integral of a particle moving in a certain space. Right? So that's where this comes from, but I have glossed over that here. Right? So you can invite me for another talk if you like. Good. Oh. Yes.
You don't show the half-odd integers. They cannot sum up to 0?
No, that's a nice question. Again, for interest of time, I have glossed over that detail here. So it turns out in the half-odd integer, do you know the answer? Or you? No, okay. For the half-odd integer case, it turns out there is a Berry phase. So you have, the particle moves on two circles, but the circles are threaded by pi fluxes. So there is the integer spin and half integer spin have a qualitative difference. For this talk, I have ignored that. So so that was perhaps your question for the other problem. So here there is a difference, but that will take some more time to explain, and so that's why I have not included that.
Please use the mic because
Yes.
So will not there be any frustration for three spins like in the Heisenberg kind of Hamiltonian for like odd spins?
So in a way, this is frustration. The fact that the spins to classical ground states are like this and not perfectly aligned. So the frustration is included in this. Right? So there is no, this is frustrated. Frustration is included. So you can see that, so spin 1 and spin 2 are not perfectly opposite to each other. They have to form some angle between them. So that is frustration. Yes. But sorry, I interrupted you with this question. Yes.
In the statement that you are trying to prove, the original statement, that it behaves like a classical particle.
Yes.
Yeah. So what does it mean, the last statement, the particle that moves on the space of classical ground states? The last part of this.
Yes. So this is what this means. So let's say we take the dimer. So let me again just use examples because it might be easier to understand. So in the dimer magnet, when I look at it classically, I can understand how to minimize energy. And then I just look at the set of all such minima. So that's a space. And here that turns out to be equivalent to a circle. Now I imagine there is a particle moving on that circle. So there I can solve for the energies of that particle. That's what it means. Is this clear or not? Yes. Of a single particle moving on some space. So that space is a space of low energy configurations. Right? So if you've taken any course, or you might know that single particle physics is much easier than many particle physics. So these magnets are all many particle physics. So in reality, it should be complicated. You have 3 magnets. It's not easy to solve. So you have to solve it numerically. But the power of this principle is it maps that to a single particle problem, single particle moving on some space. As far as low energy physics, not just ground state.
Low energy.
Low energy physics is concerned, yes. It's a quantum particle, yes. So a particle moves according to quantum mechanics, yes. Good. Good, okay. So let's go ahead and let's come to the interesting case, which I haven't come to yet. And here is the interesting case. So the same principle applied here shows something very beautiful, very interesting. Okay. So here I have the next member of this family. I have 4 spins on a tetrahedron. I define energy in the same way. Every bond, every pair of spins is coupled with an XY interaction in the same way. Right? Essentially, to minimize the classical energy, I have 4 spins. They should lie on the same plane, and they should add to 0. Right? So here is the XY plane. I have 4 spins. They should lie on the same plane, and they should add to 0. So I should, if I go spin 1, 3, 2, 4, I should come back to the same starting point. Right? Now, you can easily convince yourself that to do this, you must form a rhombus. So the spin 1 and spin 2 should be exactly opposite to each other. Spin 3 and spin 4 should be exactly opposite to each other. So it's a rhombus. If you don't have a rhombus, you will not come back to the starting point. Okay? So I'll leave that to you to imagine. So you have 4 spins. I have to, let's say 4 matchsticks. You have to arrange them in such a way that you come back to the starting point. If you do that, you will get a rhombus. Okay? So you can convince yourself that that's true. You can even see from this picture it looks like a rhombus. Okay? So let's say I form a rhombus here. The condition is satisfied. I have 4 spins. They lie on a plane. They add to 0. I come back to the starting point. Right? Okay. So how many ways can I do this? Okay. So here the claim is, so I have, let's say spin 1 and spin 2 are opposite to each other. Right? So essentially I can fix spin 1 with some angle. I can make spin 1 point in any direction. Spin 2 will just be opposite of that. So I have one angle for spin 1 and spin 2 combined, given that they're opposite to each other. Okay. In the same way, spin 3 and spin 4 are opposite to each other, so I need one angle to describe them together. So I can just describe where spin 3 is pointed and spin 4 will just be opposite. Right? So I have 2 independent angles to describe them. Okay? But turns out that's not all. Okay? So it turns out in addition, there are 3 in total there are 3 discrete choices. Each of them has 2 angles. Okay, so let me just explain that to you. So I can make spin 1 and spin 2 opposite, or here I made spin 1 and spin 3 opposite. Here I made spin 1 and spin 4 opposite. Right? In every case, the other 2 are opposite. So spin 1 and spin 2 are opposite. That means spin 3 and spin 4 are opposite. Here, spin 1 and 3 are opposite. Spin 2 and spin 4 are opposite. Right? So, and you can see that you can rotate this. You can take this rhombus. You can squish it. You can rotate it, but you will never go from one rhombus to another. So there are 3 separate choices, 3 distinct choices. Each of them is a rhombus that is parameterized by 2 angles. Right? So one angle for this pair, one angle for that pair. Okay, good. So you have 2 pairs of anti-aligned spins, 2 free angles in each case, but 3 discrete choices. Okay. So many of you might know this, but here is this. So suppose you have a space that's parameterized by 2 independent angles. That space is a torus. Okay. So you can imagine I have 2 angles. So if we didn't have Badusha, you might have vadais for Haiti. A vadai would look like this. And if you have a vadai to start from some point, you want to reach some other point on the vadai, you have to move along 2 angles. Right? So you have some phi 1 that takes you here and phi 2 that takes you over the rim. Okay? So a torus is parameterized by 2 angles. Okay? And you can also view it this way. You can imagine that as a square with periodic boundaries. So I have this side and that side are identified, or just say taped together. This side and this side are taped together, you'll form a torus. Yes, it's a very important clarification. There are 2 topologically distinct vadais that are commonly served in Tamil Nadu. So you have the vadai with the whole genus 1 vadai and genus 0 vadai. So this is the genus 1 vadai. Good. Yes. or a donut if you're in Canada. Good. So here we have 3 discrete choices, and each of them has 2 angles. Right? So the set of ground states, set of classical ground states for this 4-spin magnet is equivalent to having 3 tori. There's one torus, another torus, another torus. I've depicted the tori as squares, so you should understand that the ends are taped. So you just tape this, you'll get a torus. Right? So if this is one torus, one torus, one torus. So in the first torus, spin 1 and 2 are opposite to each other, 3 and 4 are opposite. The second torus, 1 and 3 are opposite, 2 and 4 are opposite, 1 and 4 are opposite, 2 and 3 are opposite. So, and then there are 2 angles. So for instance, the x-axis here denotes theta 1, just where the spin 1 is pointing. Spin 2 is automatically opposite to spin 1. Okay. Then the y-axis shows theta 3, 1. Where is spin 3 relative to spin 1? And then once you fix that, spin 4 is automatically opposite. Right? So there are 2 angles, so you get 1 torus, but you have 3 tori. Okay. But now something interesting happens. Right? You see that these 3 tori are not entirely distinct. Okay. So there is some very interesting physics here. So let's just focus on this green line. Right? So this green line denotes a configuration that looks like this. Say spin 1 and spin 2 are pointing in one direction, let's say along the y direction. Spin 3 and spin 4 are pointing on the negative y direction. They're opposite to them. Right? So if I have a configuration like this lies in both families. I can say this lies here or there. So I can say spin 1 and spin 3 are opposite, 2 and 4 are opposite. Or I can say spin 1 and 4 are opposite, 2 and 3 are opposite. They're both allowed. Right? So actually this green line I have here actually repeats. It's the same green line here. Okay? So I have 3 tori, but this line is common to 2 tori. And if you look at it more carefully, there are actually pairs of this. This red line is common to this. This black line is common to this. Okay? So you actually have 3 tori, but every pair of tori shares one line. Okay? So let me show this other picture. So this is one way to visualize this, just for visualization purposes. So imagine I have 3 vadais, so 3 donuts, and I have one big vadai that's in blue and 2 vadais inside. Okay? And this is a cross-section view, right? So actually the vadai goes in, comes out, goes out this way. I've just sawn it in half, and I'm just showing you the cross-section. Right? I hope that's clear. Okay. Now you see that the big blue vadai and the yellow vadai share this black line. It's actually a line that goes in, comes out, and actually will complete a circle. Right? Similarly, this red line goes in, comes out there, it'll come out and complete a circle. Right? And then these 2, they share this green line. It'll go in here, come out there, complete a circle. So you have this kind of some very interesting geometry shape, 3 tori that are touching along lines. Okay. So this is the space of classical ground states. Okay. So let's just appreciate this space for a bit. So this space is very special. Well, no, it's not very special. It's there are many states that are special. Okay, let me just go ahead. This space is a non-manifold space. So let me explain what I mean by that. So let me first give you a simpler example. A figure of 8. So imagine I have a figure of 8. A figure of 8 is also non-manifold. That's a much simpler non-manifold. This is a more complicated non-manifold. So let me just explain what I mean by non-manifold. So let's just take the figure of 8. Okay? Suppose you're sitting somewhere there. The space looks one-dimensional, right? You can move left or right. There are 2 directions to move. That's one-dimensional, right? But once you come to this common point, now there are 4 directions to go. Right? It's no longer one-dimensional. But nor is it 2-dimensional. You can't move in 2 directions independently. You can only move along 4 directions. You can't move left, right, up, down. So it's neither 2-dimensional nor 1-dimensional. Right? So dimensionality is ill-defined at that common point. Right? So this space, the figure of 8, cannot be assigned dimensionality. You cannot say it's 1D, you cannot say it's 2D, it's somewhere in between. So that's why it's a non-manifold space. Right? A manifold by definition locally looks like R to the power n, some real space here. So this is not, it's a non-manifold space. This tori, 3 tori, is also non-manifold. So suppose you're somewhere here, you can move in 2 directions, space looks 2-dimensional. But if you're sitting at one of these intersection points, now you can move along the blue torus or along the pink torus. And now it's neither 2-dimensional nor 3-dimensional, it's somewhere in the middle. Okay? So this space does not have well-defined dimensionality. Okay, so now suppose I have a particle that lives on this space, and I want to explain the physics of that particle. Okay? Now, this is very difficult. If you know the rules of quantum mechanics, you should see that this is difficult because you cannot use calculus. For instance, you cannot define a gradient operator on this space. Because you cannot define a gradient operator, you cannot write a Schrodinger equation on this space, usually. So the typical conventional way of doing quantum mechanics doesn't work anymore. You have to use some tricks. So anyway, we use some tricks. So there is a simple trick. Simple trick is simply discretize the space. Make a mesh of this with the appropriate connectivity. So the red, if you're sitting here, there are 4 neighbors. You can move up this way or that way. If you're sitting there, you can go this way, but the same red point repeats here, so you can move other directions too. So we make a mesh to solve this, and we can imagine the particle moves from each side to its neighbors, and at the singular lines, those intersection lines, the number of neighbors is greater. You have more neighbors. Okay? So this is called a tight binding model. This can be easily solved. So we solve this numerically. Okay? So we claim that this explains the physics of a particle moving on that space. And yes, sure, yes.
Like only these green lines appear twice, or so if you apply periodic, then there should be more angle which will be. So is it just for these values of thetas and something?
Yeah. So this green line repeats twice. It's here and here.
Yeah.
Right. But actually, that's only one green line, right? So you should, in the picture, it looks like they're separate, but the way we make the mesh, there is only one green line.
So only these 3 lines repeat, or there can be any
only 3 lines repeat. That we can check. Only the 3 lines repeat, nothing else repeats.
So if you're applying periodic boundary condition that to make the square a torus, so will not that be other lines appear? Because
no, you'll come back to the same. So you go up here, you come back to that green line again. So it's as if you go up, you come back, it's the same green line.
Okay.
Is okay? Yes. Okay, good.
So is it like a square, like?
The ends are identified.
Yes.
That's
Yes. Yeah. It is like 3 squares, but the squares have common lines. Yes. Good. Okay. So when we do this, once again, it matches, right? So here, the white squares are the quantum problem. So we take the magnet, we do the bona fide quantum calculation, we find the energies. Those are the white dots. The blue dots, the blue diamonds come from this mesh solving for a particle moving on this space. And you can see they match, not perfectly, but not too bad as well. So the numbers match. So there is some discrepancy, but we get a reasonably good match. Okay. Sorry, can you just?
The error is because of the numerical simulation.
There is some more detail to that. So let me not answer that now. Right? So I can answer that over Badusha later at the high T. Yes. Okay. So the error is, there is some subtle reasons why there should be an error. So and as S increases, the error becomes smaller and smaller. So that is not so easy to explain. So I will escape this time. Good. 10 minutes left. Yes. Good. Yes. Good. Okay. So good. So it matches. So once again, this emergence principle holds. You have the XY tetrahedron at very low energies. It looks like a particle moving on that very interesting space where you have these 3 tori that are intersecting along lines. Okay? But that's not the end of the story. Okay? Because when you look at the particle, so if you look at how the particle moves, there's some nice surprises there. So here is, for instance, the nature of the ground state. Okay? So this is just that particle moving on that space, that tight banding mesh problem, and the lowest energy state. And this is just how the probability is spaced. So what's the probability of finding the particle? Right? So you see that the probability is very high along those common lines. It is very low in the middle. Right? So probability is not even. Okay? So in fact, you see that the probability is highest along those singular lines. And as you move away, the probability decays exponentially. Okay? So if you have a very large mesh, actually probability will be essentially 0 in the middle. Okay? So these are what in quantum mechanics, such states are called bound states. Okay? They form bound states. So to explain this, let me give you a simpler analogy that if you've taken a quantum mechanics course, you've seen, but even otherwise you should be able to appreciate. Right? So let's imagine there is a particle moving in one dimension. Right? And let's say there's a potential, and the potential is a very sharp well, it's essentially a Dirac delta function. Right? So we can imagine rolling a ball on a one-dimensional alley, and then suddenly there's a hole, but there's an infinite hole in the middle. Right? So if you have a classical ball, you throw it, the ball will just fall into the hole, right? And it'll stay inside the hole forever. Right? Classically, it won't come out. But quantum mechanically, the particle can leak out. Okay? And this is what the wave function looks like. The wave function exponentially decays on both sides. Okay? And we say this is a bound state. So this is the quantum analog of the ball getting stuck in the well. Right? So the probability is very high there, but there is some small probability outside. It decays exponentially. Right? And you can see why this happens. So there is the Schrodinger equation. So technically, this is a very simple equation. This also allows for exponentially decaying solutions. But in usual quantum mechanics, say something like particle in a circle, we neglect exponential solutions because they're not normalizable. But once you have a delta function, the derivative can be discontinuous, therefore a bound state becomes allowed, so you find this bound state. So you take a quantum mechanics course, the first course you probably study this. You'll see that a bound state forms. Okay? But the classical way of thinking is, you can easily understand why. There's a hole, then of course the particle will get stuck at a hole. It won't roll away. Good, okay. So here we say the particle forms a bound state, and we can imagine why it forms a bound state. Because there is a hole, that's the potential energy is very low there. So the energy is lower due to the potential, so the particle likes to stay there. Right? So you have any kind of hills and valleys, a particle will like to stay in the valleys, so where the potential energy is low. So here there is potential energy that's low, that's why the particle gets stuck there, you have a bound state. Okay? But here is another example that's very different. Okay? Let's imagine we have four pathways, say 4 arms that emanate from one single point. So you go this direction is direction B, direction A, direction B, direction C, direction D. Right? And we just solve for a particle moving on this space. So once again, this space is a non-manifold. It's neither one-dimensional nor two-dimensional because you have this intersection point. Right? So you do a quantum mechanical calculation for this. You find that ground state looks like this. The wave function is peaked at that central node. It decays exponentially in all 4 directions. Okay. So the particle is essentially stuck in the middle. So there's a bound state there. Right? Good. And it's peaked at that singularity, at that intersection point. Right? Now, why is the particle there? There is no potential energy. So there's no well in which the ball gets stuck. Imagine you have a bowling alley with 2 alleys that are crossing. You throw a ball, classically the ball will go this way or that way. Right? Ball will never stop in the middle. There's no reason to. But the quantum ball does stop. There is no potential and it still gets stuck. Okay? So why does it get stuck? There is no potential, but there is extra kinetic energy. So this is one way to understand it, that the particle gets kinetic energy or lowers its kinetic energy by shuttling between the arms. So it can be here for some time, it can jump there, it can jump there, it can keep jumping from one arm to another. A quantum particle can do this. And you can only do that if you're in the middle. If you're somewhere far here, you cannot jump to the next arm. Right? So this shuttling between the arms allows you to form a bound state. So the bound state is formed purely due to kinetic energy with no potential energy. Right? So that's the special feature of this. Right? So we call this quantum indecision. Okay? So you can imagine that the particle walks here, comes to the central part. Now it cannot decide. It can move along A, along B, C, or D. It has 4 choices. It doesn't know what to do. It just freezes in the middle. Right? So this is one way of imagining it. So we call this quantum indecision. The particle freezes at that singularity. Right? So now, of course, this is a one-dimensional example, but the torus is actually the same. Here you can move along this direction. Once you come to the red line, you have a decision. You can keep going on the blue torus, or you can jump to the yellow torus because the red line is common. Right? So that's similar to this. So that's why the particle forms a bound state here, gets stuck at those intersection lines. Okay? So this might sound fanciful, but this has measurable consequences. If you have a magnet like this magnet will freeze in one of these collinear states. It will freeze along the black line, red line, or green line. Right? And you can measure this with specific heat, spin correlations, and so on. Right? So this is a toy problem, of course. But if you had a real magnet that had similar features, the magnet would get stuck. And it's getting stuck purely due to kinetic energies, not due to potential energy. Right? So actually, it's quantum indecision here. OK, so I think that's no, I have a few more slides, just a couple more to finish. Good. So, and you can actually see this. So again, we take this particle moving on the space. So we take so this is actually a full quantum calculation, but for very large S. Right? So you take this very large S quantum calculation, and you look at the spectrum. Right? So you might remember from the prerequisites, you see this structure. Again, you get 0, 1, 4, 9, 16, 25. You get squares of integers. The lowest one, there are 3. Then there are 6, 6, 6, 6, 6. Okay? So this is actually the spectrum of a particle that moves on 3 circles. The particle has a 3-fold choice, circle 1, circle 2, circle 3. In each case, the particle can move around. So the spectrum looks like this. Right? So the quantum energies of this magnet looks like a particle moving on 3 circles. Right? Why is that? It's because the particle is getting stuck to these circles. There's the red circle, green circle, or the black circle. So the particle is getting stuck to these circles. Good. So the particle is, so spectrum resembles that of a particle on 3 distinct circles. It is attached to one of 3 singular lines. The dynamics, we say, is non-ergodic. So it just means that the particle can move on all of this space, but it doesn't. It just gets stuck to some small regions. It does not explore all available space. Right? And this can be measured in experiments with suitable candidate magnets. Okay, that's good. So let me summarize. So I've been trying to illustrate emergence in quantum magnets with some toy models for you. So we define 2 concepts, complexity and scale. Complexity is the number of spins in this example. So we considered 3 examples. So complexity is the number of entities and the way they interact. So here it's the number of spins and the interactions between them. The number of spins is 2, 3, or 4. And in this order, complexity increases. Right? And the scale is a window in dimensions. And the scale for all these problems we used is low energies, very low energies. Right? So in all 3 cases, beautiful emergent pictures emerge. This simple problem with 2 spins looks like a particle moving on a circle. This problem with 3 spins looks like a particle moving on 2 circles. This problem that has 4 spins looks like a particle moving on that space with 3 tori that intersect. But then further, there is this quantum indecision that happens. So that particle actually gets stuck on 3, there's a particle moving on 3 circles. So there are 3 emergent pictures, particle on 1 circle, particle on 2 circles, particle on 3 circles. Right? And at low energies, these magnets look essentially, they're indistinguishable from these particle problems. Good. So that's the summary with some toy models. So going forward, we're thinking about real materials. So these, you might think these are fancy toy models just cooked out from nothing, but they're actually very common motifs in magnets. So for instance, this dimer, this 2 spins, is the building block of strontium copper borate, which is the most famous quantum magnet. It's called the Shastri-Sutherland model. This 3 spin is the part of the Skagome magnets. So Herbert-Smithite is a very famous example. Its physics is debated no end. Then the 4 spin model is again a constituent of many materials, pyrochlore magnets. This one, for instance, barium, ytterbium, zinc oxide. You have these tetrahedra that is sitting there. Right? So in each case, we have some emergent picture for that single unit. Let's say here for 1 tetrahedron, we have some emergent picture. It looks like a particle moving on 3 circles. Right? So now I can use that to try to describe the physics of the entire magnet. So that's work in progress. So we're working on that direction. Good. So thanks to all of you. So once again, thanks to all the collaborators. So the primary content of this talk is in this paper, but there is a whole series of papers that are related to these ideas of this emergence, quantum indecision in various magnets. Okay. Thank you very much. Thanks.
Thank you for finishing just in time.
Sure.
So we have
Yes.
enough time for questions. So I invite questions from the audience. Yeah.
Wonderful talk. Thank you. I'm not very sure my question is within the scope of your talk, but I'm just curious. The picture of quantum indecision, that problem that you showed, yes. I'm just curious. Of course, if you start on an indecision point, yes. If your initial wave function is, yes. Initial boundary condition is on the indecision point, I would imagine because of the stability nature of that point, it wouldn't move this way or yes. that way. Yes. I would imagine that. But if you start somewhere else, yes. Would it somehow try to avoid that point? For some reason, I suspect it would try to avoid indecision points if you start elsewhere. Is that the case?
We are working on some version of this. I can briefly tell you. So right now I have an undergraduate student who is working on a scattering problem. You have a wave packet coming in, and you can see how it scatters off. Okay. So the results are this. So of course, you start somewhere far away, you have no overlap with that wave function. So you never end up in this state, right, the indecision state. But nevertheless, you come in, you scatter off, you go back, and then you scatter off all the legs too. Yes. So you do hit that point and you scatter off that, but you don't get into this state if you're coming in from very far away. If that answers your question, yes. Yes, there are excited states, yes. So the lowest energy state is stuck there, but if it's the excited states that are elsewhere, that have weight elsewhere. So no, they can still have a non-zero amplitude. It's just that they have zero overlap with this state.
With this state, okay.
With this state, yes.
Yeah.
Can you go to the previous slides? For the 4 particle,
This one or?
Previous, like when you saw the states, like 3 collapse, that.
Yes.
So are you saying that, because you told like for the 4 spins, the ground state will be when it will add to 0, like it will make a picture, but
yes.
that one is classically. For
yes.
quantum mechanically, if you want like 4 spin add up to 0, so is these 3 will be the like ground state for quantum mechanical problem?
No. So so these 3 are still the classical ground states only.
Okay.
So the quantum mechanical problem we have to solve. So you have to write some matrix, diagonalize it, and solve it. And those are some eigenvalues which are the white dots here. Right? But if you just look at the quantum solutions, you won't get any intuition. You'll just think there are some energies that are spread out. So but the classical way, this emergence principle gives you a way to understand it. To say, it's actually a particle moving on that space. The quantum physics of that particle corresponds to these energies.
Yeah, so these are the classical ground state, but to getting this you are using tight binding model, so
yes.
which is quantum mechanical. So
yes, so there are 2 steps there, right? So when I say characterize the space, I say the space is 3 tori. That's an entirely classical argument, right? Now I say I have a particle moving on that space, right? But that particle is a quantum particle. So at that stage, that tight binding comes, so that's quantum. Does this help? So just like even in the dimer case, we first say there is a circle. Right? The fact that you minimize energy, first spin has to be there, second spin has to be there, the set of such states is a circle. That's purely classical. Now I say I have a particle on that circle. Now I have to solve the quantum mechanics of a particle on a circle. So at that step, quantum mechanics comes in.
And for the the mention you tight binding where the probability is maximum on those lines which are, so is this because like for those points the particle have more options to go, so like the kinetic energy, like
yes, exactly, yes. So that's why it is getting stuck there. That's why the probability is higher. So it's as if the particle is sitting at the node, it's exploring all these ways. So it goes a bit here, comes back, then goes here, comes back. At least that's the classical view you can have.
And also considering the Hamiltonian, tight binding Hamiltonian, but you choose the transition probability between like any points is same, like that minus t pat. So
yes,
that is same.
That is same. Yes.
But only that there are more options, like
yes.
That.
Yes, that's the only difference. Yes. Yes.
Hi Ganesh, nice talk.
Yes.
Yeah, these 3 models.
Sorry.
Am I audible?
Now you are. Yes.
Yeah. Okay. So these 3 different mappings you did, right?
Yes.
So this you did essentially to show that there is some nice interpretation in the classical phase space, essentially, right?
Yes.
So like how can we move it forward, right? Like for example, if I give you some arbitrary topology.
Yes.
So it is not necessarily that like you will be able to do a mapping and go to like find a similar analogy in that sense.
Yes. So if you give me some, let's say there's some realistic magnet, the classical, even finding the classical ground states might be very hard.
So this mapping is, if I understand, it is very restricted, right? And like one has to really go into system by system to find whether there is this kind of analogy.
So the mapping on general grounds, we believe it's true for essentially all quantum magnets. There are some caveats, but in general, we believe it's true for everything. But the question is the mapping useful or not? That might be, for some materials, it might be very tricky to find that space
exactly.
and then to solve. That's possible. It can be, yes.
Yeah.
Can be, but
In all of them, you can. I see. I see. Some robust.
yes. So like minimizing the energy of a classical spin system, that's a well-known problem. So it is. There are many methods you can. So that is not. It's not entirely hopeless. So in most cases, you can make reasonable progress. We can easily find it. So it's just some minimizing some function in some large dimensional space, and then we can find out what the shape of the valleys is. So that we can do. Usually we can do. There are cases where we cannot. We still have to struggle.
I see. Just following up another
sure.
thing, like for example, in this case, you are not considering temperature, right?
Yes.
So when you are just making this analogy with the classical particle, so of course, if you have just a simple classical particle, it cannot escape the trap in that
Yes.
sense. But if you just make, if you put a temperature,
Yes.
there is always a finite probability, you know, like to. So this is the reason why we basically map the quantum problem rather to a classical stochastic particle.
Yes.
So I was just wondering, like whether that sort of analogy also, you know,
So
like
that might work, right? So we have so here we are showing the different energy levels match. So at finite temperatures, it won't be in the ground state. It'll just be in a combination of different states. So that can be easily taken into account.
I see.
So and that will not give anything new beyond this. Yes.
I see. And then there is this final thing, and then I will just let it go.
Sure.
So this last, right, where
Yes.
you showed, right, this, what is it called? So it feels like a saddle point for me, like, you know, like there was this one, if you could just go back maybe 1 or 2 slides. Yeah, this one, right?
Yes.
So of course, the classical particle will not be stuck at this point.
Yes.
But it feels like a saddle point where the particle actually has some sort of indecision to move which way to go. I mean, of course, it will be decided eventually by the stable attractor. Still, yeah. Right. Right. I mean, some similarity is there, it seems. Okay.
Yes.
Thanks a lot.
Sure.
Okay.
It was actually a related question. So you had this very, very nice sudden complex geometry appear when you went to
Yes,
3
yes,
spins.
yes.
So do you have any prediction of how it will look with 4 or 5? You know, do you have a feeling for what kind of geometry you're going to encounter?
It becomes too complicated to give popular talks. So we've thought about it, but and so there is a way to, you know, that family of 3 magnets. It was not randomly chosen. It's so they are simplex figures. So you see that they're all any pair has the same distance in a tetrahedron and so on. So. Not in this. Yes. So it is this family. We can continue for greater ones, but it doesn't. It becomes too complicated at 5. And even one past this is too complicated. But we've done other systems, essentially chains, longer chains with Professor Bhaskaran. There we get very beautiful networks, all different. So the number depends on the couplings we have, so on. Yes. So we have done bigger systems too. Yes.
Very nice work.
Yes, sure. Thanks. Yes. Yes.
Hi Ganesh, very nice talk.
Thank you.
So I just had a follow-up question about the finite temperature thing.
Yes.
So here you're using the energy minimization, but of course if you have finite temperature, then you have to minimize the free energy, then the entropy you have to look
Yes.
at.
Yes.
So will this quantum indecision still work, or is there a regime of temperatures where it works?
Yes, a qualified yes. So in a way, because all eigenstates match, all eigenenergies match, so temperature should work. But the way we say that the quantum spectrum matches the spin problem, so that's actually a 0 temperature argument. So the spin system itself might have fluctuations that are not just quantum fluctuations. So that is still to be resolved, or still to be solved. Yes, please.
At finite temperature, there is a notion of order by
Disorder.
disorder.
Yes.
So the entropy comes in and selects some configuration. In fact, Ganesh brought another notion, order by singularity. in this context. So for finite temperature, you are right. In some new.
Suppose you have a chain of line of atoms.
Yes.
So as like in quantum, when you want to find out the ground state for this type of Hamiltonian,
Yes.
so it is just like dimers of the linear combination of dimers of 1, 2. So in thus that there is some classical analog we can consider the combination of particle moving in circles.
Yes, so it's a, yes, so you can do many things. Right? So one is you can consider the whole chain as one system, and you can ask what are the classical ground states of that, and then you can say, let's say it's a circle. The whole system will look like a particle on a circle, low energy state. But you can go one step beyond, which is what Haldane did in this Haldane's field theory for a one-dimensional antiferromagnet. So the way Haldane imagines is this very large chain. So essentially I have two spins here, they can move independently of two spins very far away. So then essentially these two form one dimer, then the next two form one dimer, next two form one dimer, and so on. Right? So Haldane uses this so he gets the emergent picture for one dimer, although he doesn't call it an emergent picture. And then, so let's say in this case, a one dimer is one particle on a circle. Then the next dimer is another particle on a circle. So you have a family of particles on circles. Then these circles somehow these particles interact with each other. So you can write a field theory for this, which is what Haldane did. So that can be done, yes. Can be.
If there are no more questions, we thank Ganesh once again for a wonderful talk.